This is the 2003 HSC physics paper. It is part of Module 5, Inquiry Question 1. Question 16 worth 6 marks. We have a student that performed a first-hand investigation to examine projectile motion. Now, the first thing you need to know about projectile motion is it's an object that is fired at an angle. Doesn't matter where it's fired, it could be from the air, it could be from the ground. And when you fire something at a particular angle, it'll have a y component and a x component that are separate to each other. So how the object travels in the horizontal direction is independent of the y direction there. You have a ball resting on a horizontal table, given an initial push at x. So at x here, we're pushing it along this way, resulting in the ball showing in the path of x, y, z. So after we push it, it reaches the edge, and then it's sort of launched off the edge of our table there. We'll get a particular range in which it moves. A data logger used the motion sensor to measure the horizontal distance to the ball when the ball was at position y, a distance of 1.5 meters from the motion sensor, it left the edge of the table. So according to this question, the ball from here to here, this distance is about 1.5 meters in difference. In the first trial, the range was 0.6. So we're saying that the ball traveled at 0.6 meters. And the graph below was used to obtain from the data logger. So we got a nice little trend here.
Okay, and we have a gradient value. So let's actually look at what this gradient tells us. Firstly, the gradient tells us distance, and it tells us time. Okay, so what we know is distance is, in this case, because it's traveling on the table. So it's traveling on the table, and that's our SX distance there. Okay, let's call it 1, because our range here, number 2, that's the kind of one we measure once it leaves the table. So let's just call that SX1 first, so we don't confuse anyone. And then we have time, T. Okay, so knowing from how to derive a value for the gradient, it's rise over run. And if you have a look at what's the rise, that's SX1, so the horizontal displacement on the table, and we have time. Okay, so what formula matches that? Well, nice little one here. If you actually recall from your kinematics equation, Sx equals ux t. So the gradient value that we get is ux. Another way you can think about it, besides just using the kinematics equation, or still actually a kinematics equation, think about when we talked about in year 10 when we said velocity equals displacement over time. Now, this is true if you have an average velocity, which means that there is no acceleration and that there is no friction on the table, obviously. So that's a good thing. So what we can find is that ux, so ux, or the gradient value, is just 1.85 meters per second, because on this graph here, the slope is 1.85. So that is also our horizontal velocity. Now, in question B, it says the experiment was repeated with the ball leaving at different speeds. Graph, so there's the graph there, the relationship between the range and horizontal speed. So just before I get into the actual graphing, let's just look at what we actually put when we're graphing. So if I just redraw the graph here, anything on the y-axis, so that's our y-axis, that's our x-axis, anything that you are measuring, that will be the dependent variable. So the dependent variable is where you put or the y-axis is where you put the dependent variable. The independent will go on the x-axis. Okay, so if you read carefully in this question, it says you're using a different speed. So if you're using a different speed, that means the horizontal velocity is your independent and your range would be your dependent variable. So horizontal speed, and I'm gonna put the units, and then we have the range, and then we have the range in meters. So there's that. We have to graph that trend out. What we do know is if we look at the equation, Sx equals uxt. Now, the assumption that I know is that time is going to be constant. Okay, so let me just quickly divert before I get back to the question. You see here, the thing that affects how long it takes for the object to fall down is Sy, so the vertical displacement. If I haven't changed the height of the table, if the height of the table, I don't know, let's say randomly it was, 1 meter. If it is always dropping at 1 meter, no matter how fast this object is going in terms of ux, it will always fall at the same time. So time falling is same if Sy stays the same. Okay, so that's what we know. So if I know that time is going to be constant, then I can actually show you a nice little thing. So let's assume that because time is constant, it's equal to a value of 1. So that means Sx is directly proportional to ux. So if ux increases, Sx will increase with it because t is constant. It's a value that's not changing. So to maintain the ratio of this equal sign, if ux increases, Sx has to increase with it. So we know that ideally it should be some kind of straight line slope up like that, because that's a linear function if they're directly proportional. Okay. It says, next bit, identify your graph, the results from the first trial. So the first trial, I know, so the question from first trial, we know 2 things. We know that the range was 0.6, and we know that the horizontal velocity was 1.85 meters per second. So if I just quickly do a little random graph here, so I go up by 0.2, 0.4, 0.6, 0.8, and then 1.01. Okay, and then along this line we go 0.5. Obviously, when you're doing this, try and ensure that the spacings are equally separate from each other. As you can see from what I've done, they're not quite separate, but try and even them out as best as you can. Use a ruler if you have one when you do these kind of questions. Okay, so, and also these little lines, just point them out when you're drawing the graph, just to show the examiner where the specific dots are. Now, 1.85, that's roughly this point here, so I'm just gonna put that number down because it wants me to link it up. And so it'd be 6, 1.85, rough estimation from look, it looks like that. Okay, so now that I have that, I'll just draw the general trend line that I think it will follow. and it'll go something like that. It's not too bad for drawing a straight line free-handed, I think. Okay, so that explains the kind of trend we see on this graph. Question C, it says the apparatus described in this first-hand investigation was used to carry out the identical experiment on another planet. Acceleration due to gravity is less than that on Earth. So, we have the acceleration from Earth. Okay, that acceleration is bigger. That acceleration is bigger than the acceleration of this a planet. Let's just call it. Okay, just keep that in mind. The horizontal speed of the ball left the table exactly at the same speed. Compare the range. Explain your answer. Okay, so firstly we need to compare, and then we need to explain, justify our answer. So I'm just going to do this in sort of highlighted ways just so you can see. You don't have to follow this exact formatting of a response, but this would be ideally what you would like to do because you want to paint the picture really clearly to the marker. So you want to do, I'm just going to write comparison. That's just so the examiner knows that I've done the comparison. Okay. So my idea is, okay, so the comparison would be the range on planet. Okay, that range would be bigger than range on Earth. Okay, so that's the comparison I've done there. Now I need to explain this answer. Okay, and this will require you to use some kinematics equations. So I'm going to using this thing. Really doesn't like me today. Whoa. Okay. So using sy equals uyt plus ayt squared. Okay. We're going to do a couple of assumptions. So we're using this formula. We all know because uy is 0. Okay, the reason why uy is 0 is this projectile is being launched out at an angle of 0. So if it's being launched at an angle of 0, there's only a horizontal component. So there is no vertical component for velocity. Asterisk initially, at least. It does increase, or its vertical velocity does increase as it is affected by the gravitational field. Okay, 0. And we also know that, what else? And we also know that AY, or because that, and because SY is constant. So they're falling from the same height because it is an identical experiment. Okay, we can rearrange the equation so it becomes SY equals half AYT squared. If I want to make t the subject, it becomes t equals 2 square root of 2sy over ay. Now we know that asy is a constant value, so if it's constant, we can also assume it kind of acts like the value 1. And because 2 is also a constant value, we can also assume it's also just another constant. So we can say that t is inversely proportional or proportional to the square root of 1 over AY. Okay, so 1 over AY. And because we already know that the Earth's acceleration is bigger than the planet's acceleration, then we know, therefore, time on planet will be longer than time on Earth. And you can put some numbers in if you need to check that out. So we know that the acceleration due to gravity is 9.8. And let's just say the acceleration of the other planet is 1.6. Plug that into the numbers and see if that's true. See for yourself. I might do that near the end once I've done this explanation. So because the time of, or trip time of the planet is bigger than the trip time for Earth, therefore according to this equation, okay, as follows, that's our equation. Therefore, the displacement on planet is bigger or longer, you could say, than displacement for that on Earth. And that's how you do it. So just to finish off, perhaps I'll just do a little comparison with the numbers. So let's do that quickly. So if time is that, you have 1 over, let's say 9.8, because that's the acceleration due to gravity on Earth. That's 9.8. And we have a time of roughly 0.319 seconds. If I then do a different one, so time, that's Earth, T for planet, 1 over 1.6 or 1.3, whatever number you want to use, just make it smaller than 9.8. And that time is 0.791 seconds. So you can see the planet has a longer time already. Now, assuming that we launch it at the same speed, so according to the question, UX was 1.85 seconds. So SX, Earth, is 1.85 times 0.319, and SX planet equals 1.85 times 0.31, 0.791. So you have the displacement of 0.59 meters roughly, and then you have on this side 1.46 meters. So that's just more like the numerical way of doing it. And that's how you do the question.